Actually, we're just going to keep motoring forward. So effort times our effort arm equals our resistance times our resistance arm. And remember, it's the perpendicular force to the actual fulcrum. So we are now going to see my incredibly poor drawing skills. So we have an arm being held at 90 degrees. There's a hand that happens to be holding a ball, okay? The bicep is going to be lifting upwards and pulling upwards, and probably what here is going to be what is an 86-degree angle. That's not obtrusive at all. Okay, wow, that's special. Okay, we're going to say the ball itself is going to weigh 5 kilograms. Okay. Now, the length, let's go back to draw. The distance from here to here is just going to be, we'll say it's going to be 0.02 meters. Okay, the distance from the elbow to the center of mass of the ball, and so for that fulcrum there, that is going to be 0.25 meters. Okay. Now, the forearm itself has weight, and there's going to be that center of mass there. And the hand is going to have weight, which is going to be the center of mass there. So we're going to combine them both together and say that the forearm and hand okay, and center of mass there is at point, we're going to say, and we'll go 125 meters. So that's going to be the center. Okay. Now, right now, we have everything we need. So the first thing, since obviously this is already at 90 degrees, everything's pulling up and down, we don't have to worry about doing any extra math trying to figure out what's closer, what's further. Okay. So we then are going to go ahead and remember our effort times our effort arm is going to equal to our resistance times our resistance arm. So in this example, we don't know what the effort is. We know that our effort arm is going to be 0.02 meters. Then we equal, our resistance. Well, we've got two different ones. We've got the weight of the ball, we've got the weight of the forearm. So the resistance itself is going to be 5 kilograms. We need to convert that into newtons. So that's going to be times 9.81 meters per second squared. And then that in turn is going to be multiplied by the resistance arm, which for the ball is going to be that 0.25. Then the next resistance we're going to have is going to be the forearm. So that's at 3 kilograms multiplied by 9.81 meters per second squared. And then multiply that by the center of mass, which is going to be 0.125 meters. So we have a formula that looks like such. So now, folks, what do we need to do in order to solve for this problem? But that's just going to give us our vertical effort. That's not going to give us the final effort. what do we need to go ahead and do next?
I'll be honest, I'm still a little confused, but I'm trying to figure it out.
Okay, so what's confusing you?
Um, Maybe I'm just still waking up.
Okay, that's all right. So remember, we're just working with that basic formula where, well, hopefully I don't lose this whenever I switch back to it, but if I do, whatever. Our effort times our effort arm. So that's going to be, the effort arm is the distance the bicep is essentially inserting away from the elbow, because the elbow's the fulcrum we're looking at here. Effort is going to be the force the bicep is lifting with. And in this example, biceps lifting with enough force to keep the ball stationary there. That's going to equal our resistance. And the resistance times our resistance arm, well, we've got not just the ball that's being held up and pulling down in the distance, the resistance arm that is from the center of mass, but then we actually have the weight of the hand and the forearm, because obviously you're going to have both of those put together.
How did you figure out the weight of the hand and forearm, or is that just a guesstimate?
So remember, I wrote those in. So you see the forearm and hand is about 3 kilograms.
Okay.
6.6 pound forearm and hand. So that's a pretty beefy hand and forearm, but that's not outside of it. And that's obviously the working example here. But remember, we gave you guys those formulas that you guys can go ahead and look up to figure out what would be the approximate weight of the forearm and hand, depending on the weight of the individual that you're having do it. So
Okay.
for your own projects, is remember, if we come down here, we've got this wonderful table. So if we really wanted to make sure that we're doing it absolutely correctly, we would go ahead and take the weight of the person and multiply it by, for the forearm, 1.62, and for the hand, 0.61. And then we could also figure out where that center of mass is going to be relative to the object, or to the part we're talking about.
Okay. Thank you.
No worries. Okay, so folks, that's how we end up with this formula. And so we would do the 5 times 9.81 times 0.25, take that number, plus 3 times 9.81 times 0.125, and have that number, add those two together, and then divide it by 0.02. Have any of you guys had a chance to do that yet? Thank you, Chris. That looks pretty accurate to me. So the effort is going to be equal to 141.02. Okay. And remember, guys, this can be Newton meters because we're looking at torque. Okay. Now, the bicep, this is the vertical lifting force. We need what the bicep is actually fully having to produce. So what do we need to do in order to figure that out? Notice we've got 86 degrees. So what do you think we need to do? So what we have here, guys, is a right triangle because the elbow is going to be at 90 and then the bicep is pulling at that 86 degrees. God, my drawings are horrible. I realize now, nope, there isn't a shape tool, so I feel better about how bad I did that. So what we're going to do is we take that 86-degree angle, okay? So our final value since we're having to do the trig, is we're going to come up to effectively the bicep force is going to be equal to that 141.02 divided by what's going to be the sine of 86 degrees. So it's actually going to be a bit higher. Who's got questions for me?
I'm doing the math and I am not getting 141.02 newtons meters. So I'm not sure how she got that.
No worries. Let's double check Chris's work. So pulling up my handy, guys, it's okay. It's okay. Let's go through the numbers. People make mistakes. I trusted her. No, I'm kidding. Let's just go through it. Okay. So
I just want to make sure that I either am doing it right or know what I'm doing wrong.
okay, so 5 times 9.81 times 0.25 gives us 12.2625. Okay. That's the first value we definitely have. Okay. So then we have 3 times 9.81 times 0.125. That gives us 3.67875. So if I add those two together, that gives me 15.94125. So now we're going to divide that number by 0.02. And that gives me, actually, I got a much larger number than both of you guys. I got 797.0625. So no offense to Chris, that's the actual correct answer, and that's okay. So for you guys, I'm intrigued to know how you guys, so for Taylor, you're on the right page. There's just something with your zeros place is back 1. And I think that might be because you guys probably only divided by 0.2 as opposed to 0.02. And that's okay, guys. Thank you for bringing that up, Anna. And I apologize for not just running the numbers myself. So that way, we'd be able to see them all together. So then if we divide that by open, sine of 86. So then the final number I came up with was 700. Okay, let's do this. So you can see how this is me using the calculator to go through that math. So 5 times 9.81 times 0.025, 3 times 9.81 times 0.125, adding the two together, dividing by 0.02, and then taking that number and dividing by the sine of 86 degrees. So just shy of 800 newtons of lifting force. All right, so we've got two choices. We're going to go put up the yes or the no in the participants tab where you can do the polling. Would you guys like to work on your own project joints right now? Or do you guys want to work through another example as a class? So yes, if you want to go work on your own projects, no, if you want to go ahead and do another example together. that is the chat. You guys are putting that up, not in the poll. Thank you, Emily, and at least one other person for putting that up in the polling.
Sorry, I don't know where the polling is.
Oh, go under where you're going to see participants, click on that. And then you should go ahead and see that. Okay, well, no one's saying yes, so fair enough. Thank you. Under reactions, not participants. Thank you. I think it might be the version of which that I'm running and or the fact that I'm where I'm at. Okay, so clear all drawings. Now let's have some fun. So we have the shoulder joint, okay? Goes way down here. And then in our hand, we're holding, just because I kind of smitten with the number, another 5 kilogram weight. Okay. We've got a hand over it. We've got the elbow, and we've got the upper arm. Now, what muscle is going to be what's providing the lifting force in this example? Deltoid, absolutely. So the deltoid is actually going to attach in a very acute angle. So we're going to say this right here is actually only going to be 30 degrees. Okay. Then we have the weight of the upper arm pushing us down, the weight of the forearm pushing us down, the weight of the hand pushing us down, and then obviously the weight itself. Okay. So now with the deltoid lifting at 30 degrees, we're going to say that this arm, we're going to say the arm's like mine. It's really freaking long. So we're going to say this is going to be the center of mass located 1 meter away. Now the forearm, the hand, we're going to say the center of mass is going to be at 0.95 meters. The center of mass for the forearm, we're going to say is going to be at, we'll go 0.65 meters. And the upper arm center of mass, because it's a lot closer, is going to be at just 0.25. Sorry, my cat is being weird. Meters. And the deltoid itself is going to attach at just 0.15 meters. Okay. Now, the weight of the upper arm is going to, yeah, we'll say that they're not exactly got the biggest arms in the world. It's going to be 2.5 kgs. Okay. The forearm is going to weigh 1.25 kilograms. And then the hand itself is going to weigh 0.5 kilograms. So then we're going to set this up where we're going to have the effort, because we don't know what that is, of the deltoid, is going to be multiplied by 0.15 meters, which is going to equal, and we'll go in order from left to right, the 2.5 kgs, which we're going to multiply by 9.81, which in turn is going to be multiplied by that distance from the center of 0.25. Then we're going to add the 1.25 kgs multiplied by 9.81, and then multiplying that by the 0.65, and then plus 0.5 times 9.81 times what is going to be the 0.95, because we're again looking at that meters, and then we're adding our final component, which is going to be the weight of the object, which is going to be the 5 kilograms multiplied by 9.81, and then that in turn is going to be multiplied by 1 meter because of its point at which it is from the center of mass. So then we're just going to go ahead and run all of this together to get our actual effort. And I'm going to pull out my handy dandy calculator and run it myself as well. So that way we can compare and contrast our numbers. It's all good. Yeah, Anouk, for this example, I made up every single one of those ideas. Now, don't get me wrong. That is going to be relatively realistic to someone's arm that happens to be pretty long, but pretty spindly. It's okay. It's okay. We'll go through it. I mean, that's part of coming up with all these examples is, yeah, you run them, but that's why you would use those formula in those tables to figure out your own values. So all right. So, yeah, Kristen, Anna, and Lexi, that's what I came up with as well. So let's go ahead. Yeah. Yeah, we'll do the sine function in just a moment, but we're not quite there yet. Okay, we're on the sine of 30 degrees. Okay, cool. Okay, so I've got all of my numbers here in order. So that 2.5 times 9.81 times 0.25. So we have here is the upper arm, the forearm, the hand, and then the weight of the dumbbell. Add all those together and we get this sum. Divide it by 0.15 and we get that 452.0775. So notice with the rounding, we came up with the same number. So now we would take this number and divide it by, go 3.0 trig sine of 30, which is going to give us 0.5. And so our final full force of the deltoid in this example would be 904.155 for the force production the deltoid is actually having to pull with, since it's pulling in such an acute angle. So what questions do we have here, guys? Quite possibly, because we're looking in these examples for the vertical pulling component. That's why we're doing the sine. Just remember your SOHCAHTOA. So if, come back to our whiteboard, with that 30-degree angle pulling over here, you know, we're naturally creating that right triangle. And we're interested in, obviously, the lifting force. So that's gonna be that lifting force, so hence why we do sine. That's okay, Josh, that's okay. When in doubt, make sure you run each part independently. It's easy to make an error with your order of operations. And when you make that error with your order of operations in the beginning, then it's gonna obviously throw everything for a loop. So that's why, you know, you run it multiple times, you're gonna make mistakes. We all make mistakes. Now, that's also why on your exams, when you can write in your math and you can show what your work is doing, you make sure you do what I did right here, where you write it all out. And then you can do it step by step. So instead of where I just did it in brute force and got to the E and then figured out the force there, but I could go ahead and take each of those individual calculations that I had in the calculator and effectively type it out in that way. So you can kind of see how each operation happened. And then if at some point, if you make a mistake, it's like, okay, there, when I'm grading that, will see that. Hopefully, Marlana, you're not making up your numbers, but instead you're trying to figure them out. So let's do this one little piece at a time today, okay? See how we've got the center of mass? See how we have the center of the mass position? You guys just did your anthropometric labs where you figured out how long your arms were, how long your thigh was, how long your shank was, how long your foot was. So you have all of those distances, okay? Now, from there, if you know how much you weigh and you know where the center of mass should be, you can figure out the center of mass of each of your limbs and the positions in them, along with figuring out the load they happen to be. Okay, so now we're going to go ahead and have you, yes, in your groups, work together. Now, I just want you to use one person's weight, okay? Because that'll be the person that demonstrates the movement. That's the person's weight you're going with. And then from there, I want you guys to go ahead and figure out what would be the center, what would be the mass of each of those components of their body, along with where would that's, you know, copying down that center of mass. And if that person has their lab 2 available, they can go ahead and be like, yeah, my arm was this long, my leg was this long. And from there, you can literally figure out what each of those center of masses are. And then we can come back, see how you guys did with that, see if you guys have questions, and then have you guys work together again and start to figure out what would be the forces to just hold certain positions when you happen to be doing your project. Does that make sense to you guys? Okay, so once again, copy this link, put this in to everybody in the chat so you guys can see that, as you're going to be using that to figure things out for what you're doing. Now, if you guys don't mind, go ahead and once again, put up into the chat what your group is, and I'm going to go ahead and get you guys put into those groups. Sorry guys, it scans through 2 different pages, so it takes me a few. Yeah, unfortunately, Lexi, I think you're the only one there again. So I'm gonna have you hop in with a baseball pitch group. Okay, guys. So it's 10:03 right now. Plan on, I'm gonna give you at least 10 minutes to, like I said, work on those segments. So figure out the center of mass, where that would be, and then what the mass, okay, would be based on that percentage, and work together. And obviously, Lexi, unfortunately, you're gonna have to do what you can with that group, but at least you'll have those numbers you can use for your math that will be coming up with in a bit. Okay, guys?
May
So
I may I ask a question?
yeah, what's up? Go for it.
How when we have the attachment angle, is that something that's always given for a muscle? Like, do we just have to look up what the attachment angle of something is? And then do we do anything with like the angle that we'd be holding our shoulder at as we go through the various movements?
Okay, so couple different questions there. Good ones though. Now, don't think about the attachment angle right now. Just think about right now we're just doing the center masses. Then we're going to start looking at the muscles that go into it. And you're right, how far they're going to attach from the actual joint. And those are numbers that you do have to look up, and they are difficult to figure out. From there, once you guys figure out, okay, this is where the muscle attaches, the angle portion is going to be something that you're going to have to kind of think your way through. So, when I'm holding my arm out to the side, you can see how the deltoid sits really low. In fact, this shouldn't even be a 30-degree angle. It's probably more like a 15. But then if we're looking at something like a bicep, we can see how the bicep's pulling in a pretty straight line when that elbow happens to be at 90 degrees. So that's where I'm seeing the fact that you guys are thinking it through, that you're using logic. If you're like, the deltoid pulls at a perfect 90-degree angle, like, really? Does it? Like, I'd be intrigued to know how it does that, because it doesn't really have the leverage for it. Now, so that gives you the distance from it, and that gives you the leverage. But yes, when you guys are doing your movements, none of your movements has somebody just walking around with their arms held out perfectly at 90 degrees. So for the baseball pitch, if somebody's doing the shoulder and they're doing the internal rotation, well, they've got where the arm is at. So if the arm's at 90, well, we've got to rotate just the length of the forearm plus the length of the hand and then the ball at the very end. Whereas for the volleyball spike, we're going and rotating a lot more because we're extended much more fully. And so for there, they got to go ahead and run that math appropriately. So think about, okay, logically, what muscles am I going to be using as I go through the movement? And then how am I going to be using one muscle through what part of the range of motion? And then we're going to talk about changes in speed, changes in angles, which was also part of that goniometer lab. But if we know the center of the mass and everything else, we can at least figure out what would be the general overall torque that would be required to make those movements occur. Then we got to figure out, okay, what is the effort arm? And then what is the individual muscle's effort? Does that make sense to you guys? Awesome. Okay. Well, it's 10:06 because I talked too much. Yes, Marlana, do everything in meters and kilograms. Okay, that's how we're going to be able to figure out then forces and torque, because they're all in SI units. So the rooms are open now, guys. You have at least 10 till 10:17. Don't hurry. Think your way through it. Talk about it with one another. Take your time. Okay. This is not about sprinting through it. It's making sure you understand it. As we'll have you guys go back. So we talked about obviously how to find that center of mass. We talked about how to figure out that weight. And then remember, we find the center of the mass in the hand, but you start from the forearm, you add the length of the forearm, plus that length going to the wrist. So we have here is a basic drawing of what was my training partner yesterday whenever he was deadlifting. So the bar would actually be closer to the feet. The feet would not be so big. And a couple other things are drawn kind of poorly, but we're getting the basics here. So if the center, I've got the center of the mass of the torso, which weighs 30 kilos. The arms is going to be 8 kilos together. The head is going to be 4 kilos. And the weight he was deadlifting was 180 kilos. Now, these numbers are not perfect, but we're just trying to get an idea. And we're looking at here the force that would need to be produced by what would be the glutes and the hamstrings to extend the hips. So we actually want this to be on the straight up 0 degrees. So then we have to do some trig. So in order to find the actual distance that we're going to have kind of as the crow flies type deal, and this is the right triangle. Now we're looking at our angle here, which we're going to say is a 45. So what's wrong, Kat? Kat sings us the song of her people, and then I look at her and she runs away. All right. So what we're going to have is that 45-degree angle is going to now, we're going to take, in order to find that center of, the actual center of mass straight over here, we're going to take 0.4 and multiply it by, actually of all things, it's going to be the cosine of 45 degrees. And then that's going to give us the center of mass of the torso. Oh, got a phone call there. Then we've got the center of mass of the shoulders. So we would take that 0.8 meters, multiply that by the cosine of 45 degrees, and that's going to equal the center of mass of the arms and the barbell, because notice those are both being lifted in that vertical position from there. And then finally, we would now take the 0.9 times cosine of 45 degrees, and that's how we would know the center of mass distance for the head. So from here, we would then be able to figure out our resistance arms for each of these. That's that center of mass distance. Now, we already have the resistance, so we just take that 30 kilograms multiplied by 9.81, the arms by 9.81, the head by 9.81. So what we're going to end up having, and effectively, well, cosine of 45 is 70.7. So we still don't know our effort nor our effort arm, but all of this is going to be equal to, so 0.4 times 7.07 is going to give us about, it's about 0.2828 times 30 times that 9.81, because that's the kilograms. So then we're going to do the same thing with the shoulders, only now we can effectively double it. So we have 0.5656 times what's going to be not just the 8, but we're also going to have the 180 kilograms. So it's going to be 188 times 9.81. And then we're going to add the head, which is going to be 0.9 times 0.70, or sorry, yeah, 0.9 times 0.707, which is going to give us obviously a smaller number. So now we're talking about what would be 0.6363 times 4 times 9.81. And that's giving us all the resistance and the resistance arms as we go through there. Okay? Because we actually need to figure out, okay, what's this real distance to the center of mass when we're doing the trig to figure out where it goes when we're going truly balanced. And so then for our effort times our effort arm, well, this right now we'd solve for the torque. So we'd effectively know what this combination is going to be. Then we have to figure out how far do the glutes actually attach from the center of the fulcrum. And then same thing with the hamstrings, which is not going to be very far. I would figure that's going to be probably, yeah, it's not going to be 10 centimeters. It might be 12 centimeters. So it would be taking all this and then dividing it by like 0.12 or 1.3. And so that we'd see those massive forces being that has to be produced by your glutes in order to do these movements. So it's 10:42. We're almost out of time, but I want you guys to go ahead and we're gonna get you back in those groups so you guys can finish up all of your data. If you guys are done figuring out your data, go ahead, head on out, have a great day. Otherwise, I'm just gonna reopen those breakout rooms and I'm not going to close out this Zoom until the last person leaves. So you guys can work in your group for as long as you want. I will be working on some other stuff out here and you guys can have at least that ready to go and have that progress made towards your essential chapter, not chapter, but your term assignments. So sound good, guys? Oh, no one's saying anything, so. Okay.